welcome back. Hopefully everyone had a good break downstairs. Hopefully you got to see some of the circus acts and do the tightrope. What we're going to be looking at now is a talk titled Using Generative AI to Better Understand B2B Audiences from Topic Modeling to Text Classification. This is going to be held by both Lourens, Walters, and Luca, Valer. At Informa, Lourens' team supports the research and development of B2B enablers such as acquisition, propensity models, customer segmentation models, and other analytic products using both traditional machine learning and deep learning AI. Lourens is an avid cyclist and data scientist with more than 20 years of experience in a variety of business verticals, ranging from finance and healthcare to online marketing. Luca has worked for well-known brands such as Cancer Research UK, Sky, and Walmart before joining the IIRIS team within Informa 2 years ago. He's passionate about AI, machine learning, and optimization problems, and when he is not spending time in planning the strategic direction of his team, he is fostering the creation of a data-driven culture across the organization. Please welcome them both at IIRIS Informa.
Hi, everybody, and thank you for being here today, and I literally mean in this room. We are a brand that not many people know. In fact, how many of you know or ever heard about Informa? Yeah, we are in the right place. We want to literally tell you about who we are, what we do. We're going to talk to you about how we use AI to understand audiences. We got different user cases. What I'm going to do, I'm going to start out by explaining to you what Informa is, how do we operate, what is IIRIS. We are also part of one of the sponsors of the event, so come and talk to us down to the booth later on. So let's start with Informa and what we do. So we are part of the FTSE 100. It's a large corporation. We make roughly 4 billion pound in revenue. We operate and we try to connect people with knowledge. How do we do that? Well, we have a publishing company like Taylor & Francis. Then we have Tech Target, which is going to be a new company, a merger between the old Tech Target and Informa Tech, and operating in the market access platform. And then I want you to pay attention to this side, which is event. We are the biggest exhibitor in Planet Earth. We have pretty much 700 brands, and each brand will have trade show or conferences as well as website. We operate globally. We more than 30 countries. Event they go from and team they operate from Tokyo to Los Angeles. And in every day today we literally are in a call and try to solve a problem across the globe. Among the different markets we operate, we have a pharmaceutical. We go tech. Brand that you might know are the London Tech Week or perhaps the AI Summit. They're going to be in 3 weeks' time here in London. And then 3 years ago, we created a company called IIRIS. So IIRIS is one of the few horizontal within Informa. We effectively collect all the data from the different brands. We then enrich them, we analyze them, and we send them back to the brand to do what they do best, marketing and sales. So how AI come into play? So what we try to do is monetizing the use of that data. We're talking about 4.5 billion data interaction that we capture across those different brands. And what we try to do is, among the many other things, is supporting marketing activity. So for example, how do we in the B2B support a marketing team to reach out to the right audience? Not just about the audience, it's about the messaging. How do we make that message more compelling, more personalized? What do we talk to our audiences? The second problem that we try to solve is actually how we support the client. So the exhibitor, they come to the London AI Summit, for instance, and they try to reach out to audiences. What can we help? How do we help them to know more about the people they're going to go into the booth, scan the badge, and talk to them? Or maybe just people that attend similar event and they want to know about. We collect data. This is the part of the problem. We collect a lot of data through forms. And like probably yourself, when to attend this event, fill in a form by saying who you are, what company you work on, job title. Standardization across so many different sectors and job title, for instance, I'm calling myself VP or Vice President. How do you normalize? How do you standardize through taxonomy that? It's a big job when you have so much audiences, large audiences to do that. The second problem we try to solve is actually looking at understanding what people are interested in. So, for example, if you go to the London AI Summit, are you interested in MLOps? Are you interested in analysis? Are you interested in, I don't know, visualization? Knowing that is super valuable to our client. We got a couple of solutions, and this is what we're going to talk to you about today, how we use AI to resolve that. So the first one is about how we fine-tune LLMs to effectively standardize taxonomy. This is quite innovative, using Gen AI to do classification. And the second part is about extraction from topic modeling. Because we got a wealth of websites, we can track people across those websites. We want to know what they read about. But in order to do that, we need to understand what topics those websites talk about. So I'm going to pass now to Lourens. He's going to take you through the rabbit hole of the technical implementation, and then we're going to have a few questions at the end. Thank you.
Thanks. Thank you, Luca. Yes, good morning, everyone. So as Luca said, I'm a data scientist at IIRIS. And what I'd like to do today is to basically talk to you about how we've used generative AI during the past year to implement 2 different use cases that would not really have been possible a year ago before the advent of generative AI and the plethora of platforms and tools that are now available through generative AI to actually implement business use cases. So I hope you'll find it interesting. If you do find it interesting, we've got a booth downstairs opposite the coffee shop there, so please come and speak to us. Luca and myself will be there, but we've also brought a whole team from IIRIS to the actual event. So we've got our head of platform engineering, and we've also got our head of the data warehouse. So whatever your kind of flavor of data science is that you might be interested in, we've got someone that will suit your needs and that can tell you a bit more about what we do at Informa. But with that being said, let me launch straight into the 2 use cases. The first use case that I'd like to speak to you about is really one of reference data management. I think you all know that managing data is very important. So the problem that we had within Informa is really that of, as Luca mentioned, we've got a large number of different business divisions across the company, more than 600. And as you can imagine, the data that comes from those 600 different entities, is not conformed to a standard. So we have got, data governance and data management team, and they have got a reference data platform that they use to assist them in mapping this, but there's no automated way, so it's very time consuming. So the idea that we had was to automate this, and this is really the first kind of use case that I'd like to kind of speak to you about. So with regards to this particular use case, I mean, we were quite excited when the reference data management team came to us with this problem, because of the fact that they had a large labeled data set, which data scientists kind of like, because it's a supervised problem that is typically slightly more easy to solve than some unsupervised problems. So they had 100,000 labeled records that they manually labeled for us, that basically maps values from the source systems to the target values, which is the IIRIS, the data reference standard. As you can see, the problem with this kind of use case is that there's a large number of values that it maps to. There's more than 1,000 unique values, and the values to be mapped, you can look at them across ATX, west to visitor, guest to visitor. They're highly domain specific. So training a model with a high enough accuracy based on data like that requires something that is very specific. So the reference data management team tried a few different approaches before coming to us. So they have a state-of-the-art enterprise reference data unification software platform which has ML built in. Using out-of-the-box kind of ML, they attained an accuracy of less than 60%, which is not really what they were looking for in terms of assistance to do this mapping. They also tried, like themselves, using AutoML tools such as Microsoft Azure's capability to fine-tune proprietary LLMs on a virtual private cloud. But because they've also not got a lot of experience with machine learning, they also didn't really receive accuracy results that were meaningful. And then the last thing they tried to do was prompt engineering, seeing as everyone these days kind of use in-context learning and prompt engineering to fine-tune large language models. But with that, given the generality of large language models and the complexity of the actual kind of prompts that you need to generate, they didn't really have greatest results either. So we were excited to take on this. They required more or less like 80% accuracy to kind of make this viable for them as a replacement to their current processes. So what we thought of was that if we could use fine-tuning of open source LLMs to basically adapt the actual model to the actual domain that it's used for, that we would be able to create something that is of higher quality. So we looked into using Hugging Face because it's an API that's widely available with lots of support, online support for training open source LLMs. And so we went about creating a training and a test set, from our supervised, from our labeled data set. And then we decided on basically using two different types of models. So firstly, BERT, which is a bidirectional encoder. So it's bidirectional encoder representations from transformers is what the name stands for. But it's basically a bidirectional model that captures a lot of context and text and can be used to classify very accurately. It's a fairly dated model. It's got a small kind of context length, but it works really well. But we also wanted to try something more modern, like a generative pre-trained transformer. The drawback is that it's one-directional, so it's an autoregressive model that only has a context in one direction, so it doesn't capture the word kind of context as well as BERT does. But it does have a number of other great characteristics, such as the fact that it's got large context length, it generalizes better, it will have multilingual support in future. And there was a paper that was recently published that shows that you could, through fine-tuning, actually increase the contextual information it captures by fine-tuning it in a bidirectional manner, by removing the causal mask from llama. And so this paper is a link down there if you're interested in that. It's a data scientist from Hong Kong. He's very responsive also. They've listed their model on Hugging Face, and they receive really good results in terms of classification using pre-trained networks for classification. So the process that we followed to actually fine-tune the model is really to put a classification head on our kind of like transformer that we downloaded from Hugging Face, either BERT or llama, and then to use our training data, tokenize it, and send it through the network. And then depending on the type of model that we chose, basically updating the weights in as much as it's possible due to the size. And I'll talk a bit now about that. But in order to fit the larger models into memory, and then we obviously, the model will predict the target reference data mapping, so that's the kind of classification. In order to ensure that we can fit these models into memory, what we decided to use was to use LoRa, which is low-rank adaptation, which is a way to reduce the number of parameters that you actually update during the fine-tuning process so that you can actually do it on a kind of like a smaller GPU to make it viable to fine-tune large language models on kind of commercially available hardware. And the way it works, you can read the paper by Sebastian Raschke, but the idea is that there's a weight matrix that needs to be updated during backpropagation, and that weight matrix typically is very large for these large models, but it's very sparse for large language problems, so you can break it down into two linearly independent smaller matrices, and then those can be updated, and typically you will then end up with a lot fewer parameters than the original set of parameters. So how we actually used this method to actually fine-tune these different large language models that we've tested was to firstly start with the fact that we wanted as a goal to just do this fine-tuning on a single kind of GPU. It just makes things a lot easier for deploying and managing these type of models going forwards. So we chose the NVIDIA 810, but it can also be an RTX 4090. They all have more or less the same amount of memory. And then also we use the Hugging Face trainer API, which is got good support. There are quite a lot of other ones these days that are available, but we found this to be quite useful. And what we then did is if you look at the kind of the image here, is that the problem with fine-tuning is a bit like what the genie in Aladdin used to say is you've got these amazing cosmic powers, but you have to like fit it into this like teeny tiny little space to make it work. And fine-tuning is a bit like that. It's you've got these incredible kind of models that do these incredible things, but in order to actually get it to do anything useful, you need to kind of fit in a small space. So the fine-tuning, the objective really is to be able to update the parameters with this framework without running out of memory. So with BERT being a small kind of transformer, we could actually do full fine-tuning, so the one on the left here. So it used mixed representation, mixed precision representation in terms of the way it represents the data and the optimizer versus the actual transformer. But it's 16-bit kind of representation in the actual base transformer, which is which is like kind of these days the standard for doing this kind of fine-tuning. The point being that with BERT, with having a small number of parameters, we could actually fine-tune the entire kind of like a transformer for this problem. Looking at Llama, so the way we went about actually fine-tuning Llama was really to start with parameters that allow for the smallest number of trainable parameters, so maximum kind of compression in terms of the actual transformer, and you won't get great accuracy, and then just to incrementally increase until you fail. Once you then fail, what we then did is we went on from LoRa to QLoRa, it's quantized LoRa. So you start with LoRa with 16-bit representations in the transformer. With QLoRa, you kind of downscale that to 4 bits, which you should actually lose some accuracy. But in our case, you didn't really, so the accuracy was more or less the same. Training is slower, but you can end up with about 90 million parameters in the actual model by using the quantization. So in terms of the results that we achieved, we believe we achieved very good results. So as you can see down there, for Llama, we basically met the goal of 80% accuracy in terms of this data set. And if you look at the actual learning curve, you'll see that on the left-hand side, the kind of loss reduces substantially below the first 10 epochs. And this is typically what happens during fine-tuning. Like fine-tuning for longer periods don't really make much of a difference. And the accuracy curve also kind of increases quite substantially below the first 10 epochs. So it doesn't really help to train beyond that. If you look at the accuracy kind of that we achieved per kind of class, you'll see that some classes received we actually attained a much higher level of accuracy, so job function as well as property type, audience level. So and then there were some lower ones such as industry. So this was just our first kind of stab at this, but we were quite pleased with the result and feel that we can probably like increase the accuracy even more by looking more at the data and finding ways to to increase the accuracy in specific categories. So in terms of deployment of this model, it's fairly simple. All you need to do is you need to deploy it on the same kind of architecture that you trained it on, so it's NVIDIA A10, but it's not very costly. I'll give you some costings in a bit later in the talk. And then it's a simple case of just loading the model and the tokenizer from the model. And so there's some code here if you're interested in it, but it's once you've got the tokenizer loaded, you basically just give it the text and it will basically tokenize it for you, and then you give the tokenized inputs to the model and it will generate the logits, and you take the softmax, you get the probabilities, and then you get the class. And then you can basically generate the different classes as we just sent a batch through. So you can run it either in batch, so the reference data management team basically their process consists of a batch process where they run through a new batch of records, and then they map them, and then they quality check them. But you can also do it in real time because the model basically predicts very quickly. So that is more or less the end of the first use case that we implemented. The second use case is that of topic modeling, and this use case really hinges around The problem where, in our business, we've got, a large number of different business verticals, and the information on their websites, is quite dramatically different. For instance, in the farming kind of industry versus the aviation industry, the actual web content, differs quite substantively. The problem is that not all the web content is tagged. So in order to actually create or derive audience intent, you basically need to automatically, or you need to tag these websites. So the solution that we came up with was to create a topic modeling system that automatically tag these websites. Now, the challenge with topic modeling really is the domain specificity. So topic models that are out there don't do very well at generalizing across domains specifically, like if you use large language models, similar problem to the previous one. And on top of that, the consistency of the actual topics that are generated, you typically would like to look at topic trends over time, so you don't want topics to kind of over time, to change over time. Another problem with topic modeling is that it's an unsupervised learning problem. So validation is typically difficult with unsupervised learning problems because you don't have a reference data set. So you need to find some internal validation mechanisms, or also validation by subject matter expert to actually understand whether your topics make sense. Data pre-processing is typically quite demanding, so especially for traditional NLP, there's a lot of pre-processing that needs to go into the text to actually get the algorithms to work. Hyperparameter sensitivity, you change small hyperparameters, and then the kind of results are vastly different. And then scalability due to complexity, so algorithm complexity is quite high for most of the kind of topic modeling algorithms, so you need to take that into account. And then also, you need to update your topics over time. So, content changes, and you need to have a way to consistently manage your topics over time, really. So those are some of the challenges. So, like in the face of all these challenges, what we thought about was, let's look at the history of natural language processing and see if we can learn anything from, what has been done before in the field. So surprisingly, NLP has had a very long history. So since the 1940s, there have been a practice of natural language processing. In the 40s, ironically or funnily enough, the first kind of point of departure was representation learning, and the notion that kind of a word, the meaning of a word can be derived from the actual from the kind of where the word appears in text. So, the phrase "a word is characterized by the company it keeps" was kind of like coined during that time, similar to human beings do. But the idea was that you can encapsulate semantic value in terms of capturing the positioning of word within text. And so the n-gram model was really basically predicting the nth kind of word based on the n-1th words in 1940s. And the LLM kind of semi-supervised way of training, on a large corpus of data is exactly the same. So we've kind of gone back to where we started off from. But in between there was like a lot. So there was the winter, AI winter, where disillusionment in machine learning, so focused more on ontologies and structured deterministic ways of practicing natural language processing. Also grammars, so like Chomsky's like universal grammar kind of notion, was very popular. Somewhere in between, there were also more analytic ways. So rather than learning from empirical data, using mathematical distributions. So in the 2000s and 2010s, algorithms such as the latent Dirichlet allocation algorithm, where you use a mathematical distribution to basically model the underlying latent topics, within the corpus, that gained quite a lot of kind of popularity too. So based on this kind of large tool set that one has, and based on the problem that you have with topic modeling in terms of large language models and the generalizability and the need for domain specificity, we decided that a combination of the LDA algorithm, as well as which provides kind of the more domain specific kind of nature to topics, as well as using the generative pre-trained transformers for the expressiveness that their conversational models has. So the solution that we came up with was one that actually the framework has been created by Martin Grotendorst, which is called BERT Topic. So it's using a combination of large language models. So it's using the embeddings from large language models to cluster topics. But we decided, to kind of fill in, our own kind of algorithms in the kind of, the framework that makes sense for us. And so we'll talk a bit about that. But the idea is that you put your data in the one side, and then the topics come out the other side. So just going into this a bit. So if we look at, how we deal with domain specificity, what we do is we first generate topics using LDA on all the different domains. You only have to do this once, but for instance, for aviation here, we've got like around about 250,000 web pages for the aviation kind of business domain, and the documents are typically from about 350 to about 1,000 words, which is 1 to 3 pages. The idea for us was then to build an LDA model in the way that we've kind of explained before, have a training validation set, which is not often done for unsupervised learning, but we then have both internal validation in terms of metrics that tell you more about how the topics cluster, not necessarily that they're meaningful, but then we also had external validation that was done by subject matter experts to tell us whether the actual topics are sensible. What we found was that for specifically using bag of words, that the subject matter experts quite favorably kind of viewed the topics generated as in terms of being useful, and then also, I think you can see from the actual diagram here that the topics are fairly well separated, and there are quite a few topics that are picked up, from the corpus. That was encouraging for us. So once we've got these LDA topics, and we're happy with the fact that they capture the domain specificity of this actual vertical, what we then do is we combine the domain-specific topics with the embeddings from the actual large language model. So in the diagram that you see here, what we have at the bottom, we've got the two different documents. The documents are typically fed through the large language model. In this case, it's BERT, but it could be Llama. It's tokenized. There's embeddings that goes through the transformer. And then the final layer of the transformer basically captures the meaning of the document, which is then summarized in the kind of single token in the encoder transformer. What we do then is we generate topics from our LDA, and we combine W1 and W2 are the topics generated from the model, and we average the two, the embedding from BERT with the one from LDA, and that then becomes our contextualized representation of the topics for the corpus. And this can be applied to both BERT or Llama 3. And there's a paper that I've actually referenced here, which also explains this method of combining embeddings. So how do we know that this actually worked? Well, we can generate the topics before and after actually combining the embeddings, and that's what we did. So here we created embeddings for documents just using BERT, and you can see that the silhouette score, which is a metric that if it's closer to 1, it indicates that the topics are better formed. And then there's the embeddings that we used after the combination of the two, and the silhouette score for the topics after the combination of the two, is better. And we also, had our subject matter experts again look at the topics, and they did, agree that the topics are improved. So the next step of our algorithm really is to use these embeddings to actually create topics. And the way in which we do that is because these embeddings are high dimensional. In order to cluster them, you basically have to reduce the dimensionality. So there are lots of algorithms you can use for that. We ended up using UMAP. We basically reduced the dimensionality to about 15 dimensions. And then we clustered them using HDB scan, which is a nice algorithm to use because it deals with outliers. It also determines the number of topics. So it's not like k-means that you have to specify how many topics there are, and it can cluster complex shapes. So we've actually attained quite a nice. You can see here actually, this again shows that this is the clusters that were formed just by using BERT, the large language, and this is the contextualized clusters using BERT and LDA, and they're much better separated. So then the next step in the algorithm really is to use these clusters to create topic descriptions, because now we've got the clusters of the embeddings, but we don't know what they mean. And the way in which we do that is by using a class-based TF-IDF kind of algorithm. TF-IDF, term frequency, inverse document frequency, is a kind of word embedding that can assist you with finding the relative importance of a word within a document, within a corpus. But using class-based TF-IDF, which is that kind of formula there, it provides you with a relative kind of importance of a word within a cluster or a topic cluster. So that's the formula there. And again, it's Martin Grotendorst's, kind of like method. But what you end up with is these clusters. These are your topics, and that's topic number 2. And you can see that the words are ranked there, in kind of like descending importance. So there's route and launch and destination and start, carrier, schedule. So if you go through those words, basically you end up with a topic that kind of means airline routes and schedules. So it kind of makes sense, and this is how you then kind of determine what the most important words within each topic is, as well as the most important documents. So how we then kind of transform these words into topics is we then use a conversational kind of large language model, and we use prompt engineering, so in context learning. So we give it the top 5 documents or the top 10 documents, and then the top 10 most relevant keywords, according to the template. And then we end up with surprisingly meaningful topics. So again, we had the kind of subject matter experts look at this, and in most cases, this actually quite closely resembled some internal taxonomies that they had, which was useful. So the last part of the actual problem then is to deal with the fact that a lot of these topics actually are very similar, and it doesn't make sense to kind of it dilutes the kind of the usefulness of the solution if you calculate, the interest in a specific topic, if there are several topics that are the same. So what we did to resolve this is the topic vectors are embeddings, so you can cluster them together. And we used a hierarchical clustering for that. So we used a linkage function of Ward and a dissimilarity function of cosine. So we just did a normal kind of agglomerative hierarchical clustering on them. And then what you find is that the actual topics that are most similar are mapped, are kind of like combined together. And you find that, if you actually read through the topics here, you've got routes at the top, from the top down, all about route planning. And at the bottom here, you've got service development. So you can look at the kind of the dissimilarity, whoopsie, sorry. Yeah, so you can look at the dissimilarity, the length of that kind of, the length of that, before I kill myself, the length of that, of that link there determines how different the topics are from each other. So you can see, that here the airline routes and the service developments are kind of linked together, and so you can decide where you want to kind of link topics together, and then you recalculate the CTF-IDF vectors, and you can then recalculate the topic descriptions too. So basically, what we end up with then is a list of topics associated with documents. And the last step is to train a classifier to classify, what kind of topics, are within a document. And the reason why we do this is because it's easy to. You can calculate, if you reverse the whole process, you can, for a new document, you can basically calculate, the LDA and the BERT and cluster together, and then you can find the actual topics. But the easiest is just to actually retrain a classifier. And the advantages is that there's no need for extensive pre-processing. You can classify text of varying lengths. So once you've built the topic model on web data, you can classify email data or anything else because you've got the similarity in terms of the topics, and you just need to kind of apply the function to new information, and it would then come up with results. So, and also you should be able to generalize to different languages if you actually use the model that is multilingual. But you need to ensure accuracy, and your embeddings need to have a long context, to basically cater for longer documents. So the results that we achieved for Llama 3. In terms of the classification, was that we got a C statistic of about 72%, which is fair. This is still a work in progress. This is good enough to classify topics, but we're still busy improving on this. The cost associated with this kind of method is not very high. So as you can see here, to kind of fine-tune Llama 2 costs about $70. It takes about 30 hours to train, and then inference is really cheap. It's about 60 cents to kind of infer for a whole kind of set of 10,000 documents. So it's very commercially viable. So just some other thoughts in terms of topic modeling. So there's a lot going on in this field. Neural topic models are becoming a thing now too. So variational autoencoders are doing really well in terms of topic modeling. And then another approach that we came across was like actually a taxonomy-based approach. So it's more like going back to that AI winter, and looking at ways of incorporating existing taxonomies into topic modeling. So you can take an existing taxonomy like OpenAlex as a concept, taxonomy, or IIB is a marketing kind of taxonomy, and then you can create a graph representation of the topics within that, and you can transform the graph to embeddings, and then you can use the embeddings to identify new topics or merge topics or predict or classify. And then as you build out your taxonomy, you can update the original graph, so that becomes your kind of repository of topics. It's a powerful structure because the taxonomy structure of the data provides a lot of signal for when you do text classification or similarity comparisons. So that's something to look out for. So the conclusion really is that large language models can be combined with traditional NLP to create value. So you can accurately classify short text in a large number of classes, like thousands of them. And you can also automate reference data mapping, which is what we did. And then, so the use of contextualized LLM embeddings to identify latent topics in the corpus is also something that's very achievable, and a lot of people are doing that. And then creating meaningful topic descriptions using conversational LLMs, and then managing topic taxonomies through semantic textual similarities, such as what we've done with hierarchical clustering. So potential further uses is to use the semantic similarity to find an audience with similar interests to the topics, and then also to gain a deeper understanding into audience interests, which can be an extension of the kind of work based on using contextualized embeddings to represent meaning in a corpus of text. So that's more or less it from my side. If there's any questions. Are there any questions? Sorry. Yeah.
Hi, thank you. Okay, hi, thank you. That was a really good talk. What I loved about it is I think, and this is controversial, right? But I think people get far too excited about ChatGPT and LLMs without actually understanding NLP. They don't even know that Vo is bag of words. They don't know what a cosine similarity is, things like that. So I thought it was brilliant. And I noticed, even I'm old, but even I didn't realize BOW was from 1950. Because I think I discovered it 20 years ago. Yeah. So I really liked that. And what I wonder is, do you think, what's your advice? Do we all just jump to prompt engineering, get on ChatGPT and trust what it's telling us? Or do we need to understand some of those foundation building blocks, like BOW, like cosine similarity, and you talked about TF-IDF, but maybe some people don't know. Do we need to understand those to build these better classifiers? And of course, you touched on almost like Web 2.0 and semantic ontologies and things. I know you just skirmished that. But what's your view on whether we need to understand some building blocks rather than just, you know what, here's an app, here's some code, do it, and it's a black box. It might be the best solution, but it could possibly be far from the best.
Yeah, thank you. That's a really good question. Shall I take it?
Start and then compliment.
Yeah. So thank you for asking that question. I think my take on it is that data science really is a multidisciplinary kind of field. So and there's no, in my mind, there might be some unicorns out there, but you need a variety of different skills to actually make something useful. And so you need maths and stats, computer science, you need domain-specific information and knowledge, and you need to be able to communicate. So to do anything with real meaning, depends on really, where you fit into, the bigger picture. I mean, I fully agree with your comment, around the fact that from an engineering perspective and a machine learning perspective, if you're going to be working on algorithms that work from the bottom up, you're going to need to, know the basics, because there are many things that LLMs can't do, that you need to do with other tools, and you need to have that understanding. On the other hand, undeniably, obviously, we are going to be doing things differently in the future, using technologies such as generative AI and LLMs. I strongly believe we've got a long way to go before we really crack AI. It's a big step forward in terms of LLMs, and they can do a lot of things, but there are a lot of things they can't do, and there's a lot of things that we still need to learn about how to do better. And for that, I completely agree with you. If that's where you want to be, then you need to learn, the background of the actual field. However, on the other side, if you're more on the applied side and you want to create solutions, for business applications, certainly, if you used to, there are some tools that are doing amazing things. If you learn how to do those effectively, you can be just as effective in a career, focusing on that element of it. So I think it depends on your focus. I don't think, like any scientific endeavor, it's not. We're never going to invalidate anything that's been done in the past. Any learning is something that kind of contributes to the field, and that would always be the case. Thanks.
Thank you very much. And unfortunately, we've run out of time. However, I know there's a question in the back corner. Sorry I couldn't make it over to you, and a couple others. Please go down to the booth. They are downstairs. And thank you very much. So exciting to see the opportunities that are out there.
Thank
the tools
you.
that we have.
Thank you.